So let's get started where we left in the previous video. So we were talking about this chemical analysis. We were looking at the chemical analysis part of that. So we'll look at the chemical analysis procedure, which is we talked about this direct chemical measurement, use of a sensor, and then I said that you need to do some sort of sample preparation before you go for the chemical analysis. So when we talk about the sample preparation, we'll kind of go over this. What do we mean by that? So when you say if you go and collect a solid waste sample or even a landfill leachate sample or a soil sample, you don't take that sample and directly put it in that analysis. Say whatever analysis that you're going to use, you're not going to just take the sample and just go directly into you cannot go from here to here directly put it into the instrument. You have to do some sort of preparation in between, and that's we call either some sort of physical preparation or chemical preparation. So when we say physical preparation and the chemical preparation, what does it mean? Physical preparation means you may have to mix it. Say waste is a highly heterogeneous material, so waste when you take a waste sample, they are not they are not very I would say they're just not all mixed up very nicely. You may have a piece of cloth somewhere, you may have a piece of paper or some metals and some other things in there, but that's what is the representative sample there. So if we want to get the representative sample, you may have to do some mixing, you may have to do some grinding, you may have to do some drying as well. Drying to do on the dry basis that we talked about earlier, if you want to go for a dry basis versus wet basis. But even if you have to do some grinding, first you have to dry, because we don't have wet grinders that much. Usually we use the dry grinders. So we need to do these kind of some of these mixing, drying and grinding to make the sample really uniform, make it so that when you do multiple analysis, you are actually measuring the same thing. Otherwise getting a representative sample becomes very difficult. And towards the end of this towards the end, when I think in the 9th and 10th week, when we were talking about electronic waste, again this will come, like how to get a representative sample from e-waste. Electronic waste, there are so many different components, but what is the representative sample? How to use that sample to do any testing? We'll talk about that again. So those are some of this physical preparation, just to get a representative sample, make it a more uniform sample. But even after doing this grinding, mixing and drying, you cannot take it and inject it in a machine, because if you have walked into any environmental lab, if you have not, I would encourage you to go and see an environmental lab so that you can appreciate the concept that I'm trying to explain, because why it is needed. Say if you're using an ICP-MS or a GC-MS or a GC or a simple ICP, and I'll show you some of those pictures of those. There are a small, you cannot take this sample and inject it directly there. You have to do some type of extraction. Say solid waste, we have some solid waste sample and we want to measure how much heavy metals are there. So, but heavy metals are not just freely around on the solid waste, so that we just take this heavy metal and try to find out the number. These heavy metals are bound up with organic matter. They are in some sort of complex form. So there are certain bonds are there, covalent bond, ionic bond. We need to break those bonds to make these heavy metals free. So for those things, we need to do some sort of acid digestion, because at acid, very low pH, heavy metals will dissolve. So that's what over here in terms of the chemical preparation, we have this acid digestion we have to do. Then there is something called solvent extraction. Certain things are present, but they have to be extracted, especially the organic compounds. They will be there in the sample, but you have to extract them, and you have to extract them using certain solvent. Solvent means something which will solubilize that particular compound that we are interested in. So that's your solvent extraction. Then you may have to do some chemical oxidation. Chemical oxidation, what it will do, it will break up all the organic bonds and even the ionic bonds, and then it will make things free, and then the things will come into solution, and then we can inject that in terms of the analysis, and that could be done using either titration, electrode or instrument. So there are different types of instruments are used. So this is very, very critical, especially those of you who intend to do lab-based work, or if you have done lab-based work, you definitely know this part. But if you have not and you are planning to do some lab-based work, doing good lab technique is very, very critical in producing good data. Without good data, Good data is kind of the raw material of a good design for waste management system, and that's where we are lacking. We have to have a good database of waste quantity, quality, and different types of characterization like physical, chemical, calorific value, and those should be the real sample, not the sample collected. If it's being collected from the houses, but there are changes in between, we should track the changes in between. So we should in fact collect sample at the house level, at the primary collection center, at the secondary collection center, and all the way to the disposal site, the dump site, so that we can see how the calorific value is changing, how the biodegradability fraction is changing. So all those, then we can make a good judgment in terms of what kind of systems will work in our city. So this sample preparation analysis is very, very critical, and again, this is not only for solid waste, it's true for wastewater, it's true for water sample, it's true for soil. So all these different types of samples can be used for similar concept can be used. So once you do the sample preparation, you will go for you have to use certain methods for the analysis. And then when we talk about these methods, there is a standard method we talked about. How do you know which method to use? Often they say, typically in the regulatory world, they will tell you what methods to be done, and you can use this standard methods book to find out which methods is being done. As a researcher or as a student, if you're working on your master's thesis, PhD thesis, even for a BTech project, you will do some literature review, so you will know what other people have used the methods, so that you can use similar methods, so that you can compare your information that you gather from their information, their data that they had. So those things needs to be done, and so there are several standard methods which is out there, which one of them we have like a standard methods that we talked about is like which if you go to any lab you will find that. Then SW846, I mentioned to you about that as well. Then there are some ASTM method, formerly it is used to be American Society for Testing and Material. So those are the different methods which is like a source where you can get those details and use it for your analysis. So after you have the methods, you have selected the methods, you will try to go for some sort of instrumental analysis. So there are different types of instruments have been developed in the environmental samples. There are the instruments, all these instruments, what they do, they give you a response. So we get a response from these instruments, and we use this response in terms of the analysis, and that response correlates the amount of sample present. So that response could be increase in conductivity, the response could be absorbance of light, the response could be emission of light, depending on the type of experiment. Increase in conductivity, many times you see that in terms of IC, when we use ion chromatograph, since everything is ions, means they will have conductivity. More the ions, higher should be the conductivity, and and should be higher the TDS as well, total dissolved solids. Absorbance of light, that's what AAS works on. AAS works on the principles of absorbance of light. Emission of light is what even absorbance of even spectrophotometer, your spectrophotometer that you use quite frequently in our environmental labs, that is again works on the principles of absorbance of light. And emission of light is ICP, which is uses emission of light. Absorbance of light, we need to be really careful. It's a colorimetric. It's usually they are colorimetric method. Colorimetric means which uses color, and if your sample itself is colored, then using the spectrophotometer gets a little bit tricky. You have to make sure that you're taking care of the background correction, which may be needed. So that's different instruments can be used based on different analysis. And whenever we go to do these kind of instrument analysis, first we prepare this graph. And if you are done any lab work, I'm pretty sure that you know what it is. It is calibration curve. We call it a calibration curve. Now what is a calibration curve? What we are doing over here. So this is called calibrations. We have the calibration curve. So CALIBRATION. So that's the calibration curve, and here we are x-axis is the concentration, y-axis is the response. So what we are doing here, we are increasing the concentration. As we are increasing the concentration, we are seeing a different response. These are the response points that we are getting, and then we are doing a best fit line, and you many times you hear this term r square. You get the r square number, which should be closer to 1. It's better as you go closer to 1. It's better for us in terms of the r square. So that's the instrumental analysis. So based on the concentration and its response. So here these concentrations are our we have prepared these concentrations, and we have passed it through the instrument. We got certain response. So these are the response points. Now and then we got this best fit line. So this best fit line is kind of the equation that we use for analyzing for sample. So what we'll do next, say if you have an unknown sample, you will get some response. So from the unknown, when you do the unknown sample, you get the response. So you say if you come over here, that's the response. Then you kind of go down here. So that's the concentration with that particular response. So this is how it works. So since more, and this is there for each and every instrument. So what happens is this basic like a basic principle of having this calibration curve and getting this response. So once you make your calibration curve using the different standards that you use, and then you come up with this like a best fit line. Then you go for unknown sample, you get a response, and then you have this concentration being given to you. Most of these, because of this computerization and everything, for most of the analysis, this happens in background. You don't really see it which happening. It's a software coming with your instrument does it for you, but you need to understand what is going on. Again, as I was telling you in the previous video, there is a difference between a research student, master student, PhD students, and postdoc, and a lab technician. Although I would expect a lab technician also to try to understand that, but my expectation from a research student is much higher than from a lab technician. So you need to really understand what's really going on. So if you're for some reason, if you made these standards wrong, say if you messed up in these standards, then your calibration curve will be wrong. And I have seen in some of the labs what the students were doing. They were making these standards, and they were doing this calibration curve, and then they will use one of these standards to check whether the calibration curve is correct or not. So if you had made the mistake in the beginning, that mistake will be, say, 2 mistakes since your initial standard you made wrong. Later on, if you check with the same standard, it will give you the correct number because the input is wrong to start with. So you need to really be careful in terms of. So you should make a newer standard. You should we call it a calibration check standard, and that should be made from scratch. You should make a fresh calibration check standard, and then you check whether your calibration was okay or not. Because if you made first set of standards, so you start from, say this is our 0, you start from 5 ppm, 10 ppm, 15 ppm, or 20 ppm, whatever, and then you got your best fit line for that. But then if you use the same 10 ppm to check it, if the 10 ppm was wrong to start with, the next time when you check, it will give you the correct, because what we are doing in the beginning is we are telling the machine that if you get this response, that is for 5 ppm. If you get this response, this is for 10 ppm. If you get this response, this is for 15 ppm. If you get this response, it is for 20 ppm. But if my 10 ppm is standard, I made it wrong, and that can happen. Say if you're working in the lab, suddenly your phone rang and you lost your concentration, and then rather than you added up, while you are pipetting it, you added maybe a drop more or drop less, and all based on your calculation, and then your 10 ppm standard has gone bad. So how will we check that is when you do this calibration curve, you come up with a newer set of a standard. So you make a newer data point here, you make a newer data point there, and you make this a standard as a fresh standard from this standard bottle that you have purchased, and you check it whether the numbers are correct or not. So it's the probability of making the same mistake again is wrong, it's very low. So that's why if you have made mistake in the beginning, that will be checked in the second time. So I hope it's a very, very important point. And what based on my experience of last 2 years working in India. Before that, I was abroad, but in India we are not that careful in terms of quality assurance and quality control, and that's why most of our papers, many times we struggle to get it in a very good quality journal, because we don't follow good quality assurance and quality control. We don't, and that's critical in terms of getting our research quality better. So I strongly encourage you that if this part of the video, you listen again and again if you have to. If you don't understand, ask me as many questions as you want through the discussion forum. We'll be very happy to respond, but you definitely understand that this is very, very critical, and it's true for any environmental analysis you do, even whether even not even environmental, I will say even in any experimental work that you do in any field, that it's you have to be really careful in terms of the data quality. Your data has to be good, and you have to be confident, you have to defend that why this data is good, and we'll talk about some of these aspects again in a minute or so. So I hope that kind of clears up the importance of this part. And then in terms of some examples of instrument analysis, the spectrophotometer, which is it measures absorption of light at a specific wavelength. So we use different wavelengths to measure the light. Some chemicals are directly proportional to absorbance. There are many methods that are developed based on the color change. We use in the titration as well. Can be measured using those things, can be measured using absorbance. Here you see at the bottom here we have 3 beakers, and those beakers, it's essentially for the H2S analysis. These are the H2S analysis beakers. Here this one is my blank. It has no H2S, a little bit of H2S, and then it says high H2S. So these are my kind of, as you can say, even a standard. So I'm trying to, so if I have a colored sample, so now if you look at here, this is a clear water sample, so it has no background. It's a clear water sample, so at the absorbance of light, there should not be any absorbance of light as such. The little bit of background will be there, which we can zero it. But if we had a sample to start with which was colored, so if you have a nasty landfill leachate sample which is colored, I remember I told you that nasty landfill leachate will be like a dark coffee colored, black coffee. So if we had that sample and we had to use a spectrophotometer, since so much of color is already there, it will be difficult to use a spectrophotometer for those kind of sample. But luckily what happens is, since the landfill leachate has so much, the concentration is so high, even if we take like a 1 ml or even like a half a ml and dilute it, that concentration is good enough to be above the detection limit of the machine. So we can still use it, and when it's diluted mixed with the DI water, the color goes away. Color is almost gone, so or it's a very faint color, and that spectrophotometer can be used for that. So, but there are it's a spectrophotometer. What it does, it's measure the absorbance of light at a specific wavelength. So here again we'll have certain sort of standards going on where this standards will have certain absorbance number, and that absorbance number will be used. So based on certain concentration, there is certain absorbance, and then when you do this unknown sample, whatever is the absorbance value you get for this unknown sample, and it will calculate back the concentration. Similarly, as very similar to what we are talking about in that calibration check diagram just in the previous slide. So those things happens already inside this machine right there. So this machine has that computer, it does it for you. You may not realize that, but this is exactly what happens in terms of the instrument analysis for that part. So so that's in terms of, so there are concept of quality assurance, quality control, that's a QA/QC. It's designed to make sure the data you gather are sufficiently accurate, precise, and repeatable. So again, data quality is very, very important. As I said earlier, that's one area where I see that we lack, as in general. Some people might be doing great, but in general observation that I have, our data quality, we don't really pay very good attention to our data quality. Some of them is because many of our labs are not that good equipped, but labs are getting better. We are getting good instruments, we're getting good lab, especially in good universities and good institutes like IIT, but still our data quality, that the culture of having this quality control, quality assurance, making sure that the quality is good, it's a bit missing. And that's so how we make sure this quality is good, and what are the things that typically done in a good lab practice. So when we say quality control, quality assurance, what really we mean? It's a design to make sure that the data that you are gathering is accurate, so that it's sufficiently accurate, precise, and repeatable. When we say accurate, means it's the real data, and how to make sure it's a precise. So it's and then repeatable. So if you do it again and again, you should be able to get the same numbers. So there are mechanisms of doing that. We use blank samples, we can use a spike sample, we use replicate sample, and I will try to explain each one of them a little bit. When we say blanks, why we use blank samples? What is the uses of blank? What we really mean by blank? Blank means we'll use a DI water or deionized water or double DDI water, whatever you call it, nanopure water. And so since you are using certain beakers, you are certain lab instruments, lab equipments that you are using, those lab equipments, those beakers may be contaminated. Say somebody else has used it. For example, you are trying to use some solid waste sample, but previously I had used it for electronic waste. I had those beakers which I had some e-waste going on in there. Typically e-waste means a lot of heavy metals, especially lead, cadmium, and those things will be very high. So I didn't clean it properly, or I kept it for cleaning, but you rust in and you had to use it, so you took those beakers not realizing that they are not really clean, because you will really, when you do this digestion of electronic waste sample or anything, you don't see any color or anything in there, or any like a dirt or gooey material to tell you that, oh, this is dirty, I should not touch it. They look white, they look it's a glass beaker, but it's not really clean, because when there is a cleaning procedure, we have to clean it using some dilute acid. We keep it in a dilute acid bath overnight, and then we clean it, and then we pass it through some nanopure water on DI water to make it really clean. And so if your glassware is not clean and you did some analysis using that dirty glassware, then what is going to happen? You will have the problem of this lead and cadmium showing up in your solid waste sample, because it was there, the leftover from the analysis that I did a few days before on my electronic waste. So how we'll check that, whether my glasswares were clean, whether there is no contamination coming from the lab itself in our sample? For that we use these blanks. So this is the importance of the blank sample. It's very, very important if you think about that. Because there could be contamination coming in. You never know, because and especially when we are looking at these newer types of contaminants which has very low standards. They are supposed to be, their research is suggesting, the toxicity information is suggesting that they are bad at low concentration. And when we are trying to put certain regulations on them, we have to really have this data. When we classify something as a hazardous waste from a non-hazardous waste, the cost of managing that hazardous waste goes up. Cost of managing something which we think is bad, it goes up. So but the company can go to the court, and we have to defend our data. So think about that. There could be litigation, there could be a lot of financial implications. So that's why we need to really make sure that the data that we have collected is accurate. There is no background contamination coming from the lab environment. So for that, the blank samples are used. Many times we also know what is known as field blank. We'll carry a DI water with us to the field and bring that DI water back from the field. And just to make sure that there is nothing happen along the way, especially if you're looking at some of these organic contaminants, even the exhaust from your car that you used for, say you took the back side of the bonnet out, and the car was running, there was some exhaust going on, and some of these organic chemicals from the exhaust can get dissolved into your sample. So whether those things are happening, we use a field blank. And that's is also done. So those are very, very important stuff. Unfortunately, again, as I said, in Indian context, we don't really pay much attention to these, and these are very critical, and we need to pay attention to these aspects. Then we do some spikes. Spikes, what is the spike sample? Say if you are trying to use, you are trying to analyze a certain solid waste for say arsenic, lead or cadmium or certain organic chemicals. So whether my machine is working properly in terms of analyzing these elements. Say if I'm analyzing it for arsenic, so whether my machine is reading arsenic properly or not, how will I know? So I'll take a sample. So this is my sample. I'll take a sample and I'm measuring arsenic in that. Now I'll take the same sample and what I will do is I will spike some arsenic. I'll add some arsenic, say 1 milligram per liter of arsenic I will add it. And why so this is called spiking. I'm adding some arsenic to it. And so here when I do the analysis, say I got X milligram per liter. Now here I should get X plus 1 milligram per liter because I added 1 milligram per liter to this. If I don't get X plus 1 milligram per liter, what does it mean? That means my machine is not reading arsenic properly. Machine is having some problem reading the arsenic. So to do that, this is known as the spike, and this is called the spike sample. When you add certain concentration to get the so to do the spiking of the sample to find out whether you get whether the machine is reading that particular element correct or not. So that is called the spiking. And then replicates means whether the machine is giving you the same. So this in terms of the replicates. So if I collected a sample from the field, now I'm trying to analyze it from the same beaker. I take a sample, then I take another sample, and I take another sample. So from the same beaker I took 3 samples, 1, 2 and 3. Now if I'm analyzing again, say if we are analyzing for arsenic, if I get it for X here, I should get something very closer to X and something also very closer to X over here too. They will not be exactly X because like there are some human errors could be there, but usually we try to go for plus minus 10 to 20%, especially for inorganics. So it should be within plus minus 10%. So in this, if I get X as maybe around 10 milligrams per liter, so here in these 2 samples or like in this I should get something around 8 to 10 milligram or like 8 to 12 milligrams per liter, what should be in these 3 data. If it's not, that means there is some problem. If my replicates are not showing up the same number. They should, because the things should be repeatable. That's what we said earlier. Things should be precise, that we talked about earlier, accurate, precise and repeatable. To make sure they are accurate, they are precise and repeatable, we do this quality control and quality assurance, and it's very, very critical in terms of the good data. And if you do that, I promise you that if you do these in your research projects, in your research labs, definitely you will be able to publish your paper in a good journal, which is very, very, and we need to get good papers coming out of India in good journals in future, so that we can like in other we have to compete. When we say we have to compete globally, we need to produce a good quality paper. And only paper is not important, but paper is one of the yardstick is there. And then there are this quality assurance plan. I will not read through that. It's a basic, essentially whatever I've been telling you, this is what it is. It's a QA project. It's a detailed activity. You do that. And there are standard operating procedures, sampling strategy, you do the sample custody, calibration procedure, internal QC checks and all those things. You can read through this. This material will be provided to you as a PDF. It's so these are different things we do it. And if you are interested in that quality assurance, quality control, I would encourage you to go on Google and look at that. There are a lot of examples out there. You will see them QA QC plan. You can download some reports and you can read those reports as well over there. So with that, let's kind of we'll stop here in terms of this particular, and this in terms of one of this video is one of the very, very important video, I would say, in terms of environmental in general, for environmental engineers or environmental scientists, in terms of understanding of good lab practices. And we'll continue that discussion in the next video as well. And then at the same time, try to understand having this good data quality. Data quality is very, very important in terms of coming up with your good in terms of good data. Good data is in terms of whether you're trying to go for design of the waste management system, wastewater system, water treatment plant, air pollution, anything that you do, soil pollution, soil remediation. Data is needed. Data is the raw material for design, and that data quality is important. If the data quality is bad, you may be a great designer, but if you are working with bad data, your design will come out to be bad. So with that, I would conclude this video, and we'll continue our discussion in the next. Thank you.